Hi all, and welcome to today's webinar from DIGILENT and I and our partners EMONA. My name is David Horn, and I am the Senior Market Manager for DIGILENT and I. And with me, I have Alfred Bresnick, who is Sales and Marketing for EMONA TIMS. We are very excited to talk with you today about enabling interdisciplinary engineering and being able to teach multiple courses with single pieces of hardware. So let's go ahead and dive right in. So the evolution of engineering education, a lot of you guys that were part of academia during the pandemic know that there was a big switch for, and even starting before that, but I think the inflection point was the pandemic in about 2020, and there was a big switch to remote and hands-on and just a way to get the learning in the hands of the students. Before that, in the 2000s, we saw a lot of classrooms around universities around the world starting to do that as well. So there's a lot of value in that, and rather than just lecture-based courses, we're seeing more flipped classrooms to be part of the, instead of just telling but showing and experiencing the learning. So project-based learning is really good for creating projects, for giving students the ability to solve problems, to put them in the power of their own learning, and also to teach them how to present themselves. I have a couple of quotes here from some universities that we've talked to. These are echoed across academia. You see plenty of professors that truly understand the value of how to engage their students and how important it is to get hardware into the hands of students and to give them skills that they can do, not only to help them learn, but also to take it into the workforce and industry. As you see this quote by Dr. McNair over here from Georgia Tech, you can, if you learn how to learn and you'll learn how to use what's in front of you, that's something that ends not whenever you cross the stage and graduate, but it's when you're going into your profession as well. So for those familiar with DIGILENT, you might have seen some of these before. If you aren't familiar with DIGILENT, I'm going to give a quick overview of how we engage with academic professors and lab managers in universities around the world. Our most popular product is probably the Analog Discovery 3. It's been, as you can see by the name, there's multiple iterations of this product. The most recent one came out in, I believe, 2023. And this is a great hockey puck size piece of equipment that is 12 instruments in one. And it's a mixed signal oscilloscope, and it's great for students during their homework, bringing it into class and giving them that hands-on learning. The other thing I want to talk about here is the Analog Discovery Studio Max. So this came out last year, and this is it's the Analog Discovery 3. The same software is going to be the backbone of it, which I'll cover in a second. But this is more lab ready and rugged, has more channels, does more serious measurements, if I'm being honest, and it includes the DMM and power supply, as well as the analog and digital instrumentation as well. You can see here there's external BNCs. It really tackles a bunch. And what makes this special is the breadboard is removable. And that's how we can partner with people like EMONA to create their own board for their own specific areas of learning. So a couple more specs about the Analog Discovery Studio Max. So again, it's 4 channels. We're looking at 100 megasamples per second. And the function generator is going to be 14-bit resolution and also 100 megasamples per second. There's 16 digital channels for the logic analyzer and pattern generator. It's a plus minus 15 volt power supply. It does have down here the built-in digital multimeter. So it is truly a stack of lab equipment in a smaller form factor. If you're familiar with NI and maybe have worked with Elvis in the past, you might see that it looks like Elvis, but it is half the cost of Elvis's. Elvis has been end of life, and this is the new iteration. The big difference is going to be that it's not going to have the FPGA on the inside, but it has full capability to do everything, including access to LabVIEW. So if you're comfortable with LabVIEW, you can use LabVIEW, and then DigiLent's own software waveforms is a lot lighter and easier to use. Another look at the specifications here: Bode plotter, scope, function generator, logic analyzer, pattern generator. So again, a bunch of instrumentation piled into this device to make it to where you don't need to have multiple pieces of equipment to do your lab. And I think that's the big takeaway of the value of the ADS Max is you can teach, yes, you can teach electrical engineering courses. You can also start to branch out. We have mechanical engineering courses using this for their measurements. It has a lot of versatility in how you can teach. As I mentioned earlier, you can get this LabVIEW, the LabVIEW toolkit. It's free. It's one of the package part of the LabVIEW package, the VI package. So you can just download it from either digilent.com or ni.com and still use LabVIEW. If you're not familiar with waveforms, which is the DigiLent software, it is you're looking at less than 100 megabyte download. So you can go from the download to install to measurement in less than 5 minutes. It's very intuitive. Drop down, access all the instruments from here. And Alfred is going to be working in waveforms today, so get a little live look at that. And if you want to do something more than what we offer, there's also an SDK available, Python, LabVIEW, C, and you can even access MATLAB. The toolkit is accessed through that waveforms SDK. So if you do want to use LabVIEW, you can use the waveforms SDK to pull that API. So the Canvas is the name of the breadboard, and that is what Alfred is going to be showing you. As you see in the back of his screen there, that is a different one than what you see on the screen. This one comes with every order of ADS Max, and it gives you all the essentials for a basic circuits class. When we look at what EMONA offers in their communications board, you'll see different offering on the board, and it will connect into the slot at the top of the machine, and you can just pull it out. Again, this is included with the ADS Max purchase. EMONA is a separate purchase, any EMONA canvases that they do. But this one gives you access to PMOD for sensors, LED switches, and the BNC channels, and audio in, audio out. So it gives you all the basis for a lot of projects that you're going to do. So the ADS Max ecosystem is what we are, that's the big value claim here. In addition to replacing all the instrumentation in your lab, you have access to teach multiple courses with one piece of equipment. And from an academic standpoint, that means that you don't have to purchase or manage different pieces of equipment for every course. You can use the ADS Max with the simple canvas that it comes with in your circuits labs. But then if you want to teach a communications lab or a systems and signals course, you can use EMONA's board. iWorks, who you see on the right there, they have sensor packages for biomedical and for chemistry. So you can use it across multiple fronts. To get more in depth about the EMONA part of it, and including a live demonstration of how you can use this, I'm going to hand it over to Alfred. Thank you for joining, and I'm going to let Alfred take it away and stop sharing. You're on mute, Alfred.
Great. David, thank you very much for that introduction. Let me share my screen. So, as you said, my name's Alfred Bresnik. I'm one of the founders of the EMONA TIMS company. We've been designing and manufacturing engineering teaching equipment for some 30 years. And we're the manufacturers of the engineering teaching equipment being presented today, which covers 4 different subject areas in electrical engineering, which is communication systems, signals and systems, fiber optics, and controls theory. In 2007, EMONA was approached by NI to develop a communications board for the then new NI Elvis platform. This relationship developed and grew. EMONA released some 8 different top boards or experiment boards for NI's various platforms. Today, I'd like to present and just simply show the capabilities and then demonstrate EMONA's 3rd generation boards, which were customized and designed for the DIGILENT ADS Max. The first is the DXIQ, which is a communications systems explorer board, covers from the basic analog modulation right through to the very latest digital modulation schemes and concepts in industry. The second board we'll touch on is the ESSB. This is quite a unique board designed for signals and systems, which covers and gives students hands-on experience in these very difficult math topics that are presented in signals and systems. The third board specializes in the fiber optic communications area. And lastly, a new soon-to-be released controls theory board. Now, what underpins these 4 boards is EMONA's teaching philosophy. And that is to give students a strong understanding in the underlying principles and of the theory that is being taught in class. And in the next few slides, I'll show you what that means, why our boards are not traditional panel trainers where a student turns on a board and starts an experiment, but the student is actually engaged in building the experiment by following the theory. Here is an example of what I mean in communications theory. So all communications theory textbooks, papers present concepts as equations, and they all represent these equations are interpreted as block diagrams. So this is very common in the in communications theory and controls and other areas. So in the equation where there's addition and multiplication, these are represented as blocks in the block diagram as adder blocks and multiplier blocks. What EMONA's teaching principle is it takes these block diagrams and actually brings them to life, not through simulation or through DSP, but through real-time electronic circuit blocks. So on the right-hand side, you can see blocks such as multiplier and adder. So these are not simulations, these are real circuits, and I'll show these in operation shortly. Let's look at the communications board that David mentioned. This board has over 20 of these building blocks. If you look at these, this board, you can't see AM, you can't see spread spectrum, you can't see OFDM. That's because these blocks are used and reused. They're patched by the student to actually build the experiment. So how is this? The lab manuals provide block diagrams, provide equations, block diagrams, and then patching diagrams so the student can actually implement the experiment. And here's a close-up to show an adder. If you look, you'll see there's an adder block there. There are 2 inputs to the adder. There's a red lead, which is a scope lead from the ADS Max, so the ADS Max waveforms software will show the oscilloscope waveforms for the signals at the in and the signals coming out of this adder block. An important consequence of using this block diagram approach, where one board can implement so many experiments, is that it actually replaces 5 to 10 or more traditional panel trainers, where the traditional panel trainers implement 1 or 2 or 3 experiments predefined by the manufacturers of the trainer. In the boards that we're supplying with, offering with the ADS Max, is like a bucket of Lego blocks, where the Lego blocks are used and reused to build different structures. Here, the EMONA boards have many different blocks which are used and reused by the students to implement many different experiments in that specific topic area. So from a student perspective, what does this mean? Of course, one board, which they're familiar with, will implement many experiments, but the consequence of that is that if, for example, students use EMONA's Signals and Systems board in the Signals and Systems lab, when they move to a new subject, the subsequent communication systems subject in communication systems labs, they're now looking at a board and they're already familiar with EMONA's block diagram building approach. So rather than having to learn how to use a new piece of lab equipment, they can start learning by implementing the lab straight away. From a teacher's lab staff perspective, I'd like to give this summary, which shows with each board, there are no options. We provide all the accessories and the patching leads, the user manual, which describes the function and operation of the blocks, lab manuals, which are detailed step-by-step instructions. We provide the digital waveforms software workspace files, so that for each lab, you might need particular scope and spectrum or meter settings. You load those files so that the waveform software is preset and ready for the student to start carrying out the experiment. In more complex labs, in more complex experiments where specific instruments need to be set up or waveforms and signals initiated, we provide a LabVIEW GUI. So again, the student does not spend time programming and setting things up. They go straight into implementing the experiment. So having given you covered this introduction, let's look at the 4 individual boards. So the first one is this, the EMONA communications board. So there's a close-up. As we described, a wide range of building blocks. What will this do? This board will implement some 23 different communications experiments. Now, 23 experiments is far too many for any communication systems course. So this board gives the professor the ability to pick and choose those experiments out of the 23, which might be 4 or 5 experiments, that actually match the curriculum that is being delivered in that communication systems course. We look quickly at these 23. They break up into some 4 or 5 simple groups. There's the introductory labs. Then there's a section, labs 4 to 9, which cover the core analog modulation, demodulation subjects. The next 4 cover the core digital modulation and demodulation subjects. Then there's a group of 6 experiments which are more advanced, so the professor can select particular experiments such as bit error rate or OFDM or superheterodyne and so on. The last 3 experiments cover an introduction to the concepts of software-defined radio, to introduce students to what does software-defined radio mean. I'll jump across and show you briefly the support materials for this board, which are echoed in all the other boards. Each board comes with a quick start guide. So out of the box, within minutes, the board can be up and running and used. There's an experiment manual, which provides detailed information on the operation and specifications of each block. And, of course, the lab manuals, which cover various theory, background, before heading into detailed information on building the experiment and so on. So this is how each board is supported. If I come back, that covers the communications board. The second board is the signals and systems board. Again, like the other boards, you can see there's no specific experiment patched or built into the board. It combines a whole range of functional blocks to implement this range of 16 experiments. The previous slide, this one, shows what I referred to before as a LabVIEW GUI, because some of these experiments are really quite involved, looking at the Z transforms, Laplace transforms, Fourier, building Fourier analyzers, and so on. So we provide a graphical user interface so the student can get right in and start learning and implementing the experiment. If I look at these 16 experiments, they break up into groups of signal characteristics, convolution and correlation, complex numbers, Fourier, continuous time Laplace structures, and Z transforms discrete time structures. What needs to be emphasized here is that none of these experiments are a simulation. They are all implementing real live signals. So the student actually builds, if you recall, a Laplace structure, a continuous time structure with integrators. That's what the board provides. In discrete time structures, unit delays and coefficients and so on, that's what this board provides. So the students actually patch those structures that they see in class and in textbooks. The third board is the fiber optics boards, and you can see the 1mm fibers. So this board is, again, provides a complete introduction to the concepts of fiber optic communications, which means there are digital communications concepts which first need to be covered, and that's in the left-hand side in essentially labs 1 to 7. Then on the right-hand side, the subsequent labs cover from the simplest electrical, optical, electrical interface right through to full bidirectional communication on a single fiber and WDM, wavelength division multiplexing. So the students experience can see these signals and manipulate them in real time. Lastly, soon to be released controls theory board, the context. And it covers the fundamental, the core theories associated with control, first and second order systems, stability, frequency response, and then an in-depth look at PRD control of plant. At a later stage, if you'd like to see short video demonstrations of these experiments, you can go to our YouTube channel, youtube.com/EMONA-TIMS, where we have dedicated short videos with experiments implemented on these boards. Now, before I go to the live presentation, I'd simply like to show you that on the EMONA-TIMS.com webpage, we have a registration page where students and professors can download the latest manuals and software associated with each board. And there's also a separate page for professors to download further resources, for example, such as the lab manuals in Word format, so that the professor can actually customize and edit the experiments the way they wish to teach that particular subject. And there's a quick view of the professor's download portal looks like. So at this point, are there any questions before I move on to the live demonstration? If not, I'll move on. So the first demonstration will be showing this block diagram method. I'll show individual blocks and their function, and then the blocks in combination. So let me go to and share. Stop sharing. I'll now share the DIGILENT waveforms software. So what I'd like to do is here I have the DXIQ communications board plugged into the Studio Max. And what we'll look at is this part of the board where we see an adder, and we can see the adder has 2 inputs and 1 output, and 2 gain adjustments for each input. So I'll patch signals to each input and we'll observe the output. So first of all, we're looking at the yellow waveform. We can see is a 2 kilohertz sine. Here I have on channel 2, I have a DC voltage. So I will patch the 2 kilohertz sine to one input of the adder and the DC voltage to the other input of the adder. And now I'll look at the output of the adder. So the output of the adder is, as you can see, the waveform moving up and down, is DC plus 2 kilohertz. If I take this DC plus 2 kilohertz, I'll next patch it to a multiplier, which again has 2 inputs on the left and 1 output on the right. So to one input of the multiplier, I'll patch the 2 kilohertz sine plus DC. And to the other input, I'll patch a 100 kilohertz sine. If I zoom, if I change the scope time base, here you can see the 100 kilohertz that I'll be patching. So let me patch this 100 kilohertz waveform to one input of the multiplier, and I'll patch the output of the 2 kilohertz sine plus DC, this waveform, to the second input of the multiplier. So again,
so those multipliers are 4-quadrant analog multipliers, in case anybody's wondering. They're actually real electronic circuits.
So one input is 100 kilohertz sine, the other input is 2 kilohertz plus DC. So the output, by combining these 2 blocks, an adder and a multiplier, we've created an AM modulator, where the student can make measurements, calculations, adjust them, use the waveform software to get the appropriate amplitudes, phase, and frequency. And in this case, as I've adjusted to 100% modulation. If the student looks at the time domain, and for example, if we adjust the amplitude massively, we can see what we're doing really is clipping. Let me change the time base. Let's see the real effect of this clipping if I get a larger number of samples. So here we can see clipping, and then we can see the noise. So this is a quick example where the communications board can show concepts quickly. Here is an AM waveform that's clean, and then when we clip, we can see the noise being generated. So with any experiment, a professor can choose different paths, different aspects to show the student, or for the student to explore and try what-if scenarios. Let me change the time base back to, so we can zoom in. Let me take this AM waveform that we're looking at and patch it to a precision diode. So here on this part of the board, we can see a diode, and below that we can see an RC, and further across there is a tunable low-pass filter. So the board provides a single-order filter, an RC, and an eighth-order filter. So let's contrast the difference between, just quickly, an RC, single-order, and an eighth-order filter. So we'll take the output of the rectifier and pass it to an RC. Let me zoom in. So here we can see the 100 on the scope display. We can see 100 kilohertz feeding through. And some students might say, "Oh, that's an error. There's a mistake there." No, if we look at the spectrum, we can see that due to the roll-off of the RC, there is a 100 kilohertz component feeding through, and that is seen in the time domain. Let's contrast that by patching that to an eighth order filter. You see the effect. Now we can see instantly an eighth order filter will completely suppress the 100 kilohertz, whereas an RC doesn't, and that's seen in the spectrum and in the time domain. So that there's a demonstration where I could have said at the start, I'm going to show you AM modulation and demodulation on this board. Instead, I've shown you the use of independent building blocks patched together to create an AM modulator and AM demodulator, and looking at the consequences of filter roll-off. Does that make sense? Do you have any questions?
Alfred, why are you using 100 kilohertz as your RF carrier?
That's a great question, and it's answered when we look at the AM. And that is, you see that if we're using, let's say, if we're using a megahertz or 100 megahertz or a gigahertz, the student wouldn't get this textbook image on the scope where the student can actually see the carrier signal and the time and the message on the same time base. Mathematically, omega c, which is 2 pi f, if f is 10 to the power of 5 or 10 to the power of 10, the mathematics is the same. It's simply scaled. So that's why on this board we can implement any analog scheme, any digital scheme, and we can make measurements and compare them to theory, because the board has simply scaled the carrier, scaled the RF down to 100 kilohertz. 100 kilohertz also means we can use basic patching leads rather than coaxial leads and so on. So it's really, this is designed as a teaching platform for students to be able to relate to the mathematics and the theory that they're learning in class.
And do you have any other frequencies other than 2 kilohertz to play with, like speech or something like that? Or?
Well, the DXIQ is a modeling system, so there's numerous sources. One, there's a voltage-controlled oscillator, which is variable frequency. There's also on the DIGILENT Ads Max, there's a function generator where you can generate practically any waveform at a wide range of frequencies. So again, this is, as I said at the start, a modeling system to model different forms of analog and digital modulation. And there's often many solutions. There's also a speech block here with a microphone, so a student can watch their speech being AM modulated, and then their colleague through the headphone amplifier and headphones that are provided with each board can then listen to their speech being demodulated. At this point, let me pull this apart, and I will implement a second experiment. So instead of AM, I'll implement very quickly spread spectrum and show how spread spectrum actually functions. That if you have the correct spreading sequence, the correct code, the message simply falls out. If you have a different code, that the message is not recovered and only noise comes out of the demodulator. So with that, let me patch this message, our 2 kHz sine, to the multiplier we saw previously. Next, I'll patch a 100 kHz clock to this pseudo-random sequence generator. So this sequence generator is our spreading sequence.
And Alfred, those are all the same connectors that you used in the first project?
Yeah, the same patching leads plugging into the boards. Does that answer your question?
It does, yeah.
Yeah. So here we have a message, our 2 kHz sine, and we have a spreading sequence, or we can call it a code. And I'm going to multiply this spreading sequence with that message. And what we'll see is direct sequence spread spectrum. So direct sequence spread spectrum does not have a recognizable waveform in the time domain, but in the frequency domain, we can see the spectra. Let me demodulate this spread spectrum by multiplying it with the same code. So I multiply it with the same code, and then we can see the message recovered with obviously a lot of harmonics and switching noise, which I can filter out through the tunable filter. And here we can see the yellow waveform is the original message. The blue waveform is the recovered message from the spread spectrum. But what happens if I use a different code, a different spreading sequence? And what you see is essentially noise. Let me zoom it here. So from here, correct code, a different code. And for students, for younger students, this can be a very simple demonstration of why our cell phones don't interfere with each other. Because in essence, which is highly simplified, they are each using different codes. And this explains it. If I zoom in on the spectrum, here you can see the noise of the incorrect code, and here we can see the spectrum of the message being recovered correctly. So that covers my 2 live demonstrations, live presentations for this. Are there any further questions?
Carlo, do you have any questions that you thought of during the presentation?
Yeah, thanks, Alfred. With the spread spectrum, is there any options for putting in my own codes or generating different signals to use in that experiment from the ADS Max itself? Or
of course, the ADS Max has various digital instrumentations. So all the spreading sequence is a pseudo-random sequence of ones and zeros, which can be generated in the waveform software and then output and patched in. That's why all the ADS Max instrumentation can be interfaced and used with the DXIQ. So a professor can actually look at an experiment we've created and adapt it and modify it to the way they want to teach, because they've got a huge resource here in the ADS Max itself.
Okay, all right, thank you.
So we saw, first demonstration, we saw adders and multipliers being used and then in combination with other modules. In the second demonstration, we saw a sign, message, and a pseudo-random sequence or code with the multiplier to generate direct sequence spread spectrum. And finally, we recovered that direct sequence spread spectrum with the correct and with different codes. So that ends my presentation, David.
Thank you so much, Alfred. And for those that are curious, I'll give a quick screen share and show our website and where to purchase these from. So you can either go to EMONA's website, or you can come to Digilent and you can go to mixed signal oscilloscopes, Analog Discovery Studio line, and then the Max ecosystem. So that will take you here, and this is the board, the DXIQ 45G that Alfred was working with today, but you can also see fiber optic signals and systems as well. You can also get there through the academic products part, or you can go to EMONA's website, which is emona-tims.com. So thank you all for joining, and hopefully that this was a helpful presentation to let you know how you can open up your labs to teaching complex ideas and complex courses in a simple way for your students. Andre, do you have a question? I see you're typing something. Cool. Yes, very much. Thank you for attending, Andre. All right, thank all. I'll see you again.
Thank you very much.